Hello and welcome back to Guillotined 18th Century Chemist Theater. Today we're going to be talking about some basics of atomic structure. So we're going to kind of blitz through a lot of basic ideas that many of you have as prior knowledge. But if you don't, hopefully you can get something new out of this lesson. Now we're going to start with somebody that a lot of you might not know about, a fellow named W.H. Fox Talbot. Fox Talbot was responsible for realizing that each element produces its own characteristic bright line spectra, and I'll tell you what that is in a second. Fox Talbot, known to chemists, probably more known to photographers. If you have a photographer friend out there, they might know of the work of W.H. Fox Talbot. He did a lot of work with both photography and chemistry, and well known in that field. 30 years later, Swan realized to get a good bright line spectrum, you needed ultra-pure samples. And the way this worked is you would heat up a sample of an element and analyze it in something called a spectroscope. Essentially, if you see the flame on the right there, you would put the sample in there. It would give off a characteristic color, and that light would go through a prism and get split up. Now, if you send white light through a prism, you get all the colors, a la Pink Floyd Dark Side of the Moon cover. But if you send through only a certain color, then only certain colors are going to go through the prism and get split up. And so with a spectroscope, when you excited an atom, it turned out that each atom gave off its own characteristic bright line spectrum, meaning you only saw a certain slice of the spectra. And people realized that since each atom gave off its own spectrum, that could be used for identification. So really big deal in terms of identifying elements back in the early days. And so here's some example of some bright line spectrums there. Every element is going to give off certain lines. And in modern atomic theory, we'll talk a little bit more about where those lines came from. But those bright lines there were one of the key ideas and a key piece of information for people realizing how the inside of an atom works and where electrons hang out. So that bright line spectrum, really key information to the black box of an atom. Anyway, once an element got discovered and verified, modern times, you get it approved by the IUPAC, the International Union of Pure and Applied Chemistry. But a lot of the names were given in the early days based on properties. For example, indium gave off a blue color in the spectroscope, and so that comes from the color indigo and indium. I've got a good story about indium. Make sure you ask me if you ever run into me. Other names are dedicated to places like polonium. Marie Curie named that after her homeland of Poland. And then someone went along and returned the favor for her. That's curium. 1, 2, or 3 letters. The 3-letter ones are temporary names until the element is approved by the IUPAC. And you'll see those, especially in the bottom row, 110 to 118. A lot of those are getting switched over to permanent names, which are pretty exciting. The first letter is always capitalized. The other one is always lowercase. Don't write a small uppercase letter. It's got to be lowercase. Really quickly, we'll review the idea of subscripts and coefficients. Subscripts are inside a compound. Remember the law of multiple proportions, that they're going to be whole number ratios of atoms in a compound. And so what a subscript will do is it'll tell you how many atoms of the element there are that precedes it. So there are 2 hydrogens, 1 oxygen, et cetera, across the board there. Now, the only thing that makes subscripts a little tricky is if you have those parentheses at the end with that compound called calcium hydroxide. That 2 gets distributed to everything in the parentheses, just like a normal math problem. The only way to kick this up a notch is to throw coefficients in the front. And all coefficients do is they modify everything in the compound. So you'll double whatever you had before. So very, very straightforward. We'll do a lot with subscripts early on in naming, and then coefficients are absolutely critical to the idea of balancing equations and making sure that atoms are not created or destroyed, dealing with the law of conservation of mass. So very, very useful. We'll use these a lot during the year. While we're jumping around on these atomic basics, we have the idea of protons, neutrons, and electrons. And again, once we get to modern atomic theory, we'll flesh out where the protons and neutrons came into play. We know the charges of these, probably from prior knowledge. The mass of these in AMUs are all about 1, except for the electron, which is much tinier, about 2,000 times tinier. Now, the AMU is something called the atomic mass unit. It's a totally unnecessary unit. Again, we could measure all masses in grams, but it makes a much more convenient unit at the atomic scale to make up a new unit for the atomic scale. And so don't get confused by atomic mass units. It's just like inches and feet. It's just a different way of measuring this stuff. And if you're at the atomic scale, very, very useful. I would memorize that number, by the way, 1.66 times 10 to the negative 24th. And that's a very interesting number. It will come back in spades later in the year. So again, when we're dealing with tiny things, AMUs are awesome. I would not measure your mass in AMUs unless you're looking for a fun factor label challenge. Gauntlet thrown. And so again, you can quickly figure that out yourself, that it would take a little under 2,000 electrons to equal the mass of one proton. And so again, this quickly comes to the realization that most of the mass of an atom is going to be in the nucleus, because that's where your protons and your neutrons are. Your electrons on the outside of that. So this tiny little nucleus, 10,000 times smaller than the radius, has essentially all of the mass of the entire atom in it, which again, kind of mind-blowing. Atoms are small. That may or may not blow your mind as statements go. Most of them are between 1 and 10 times 10, 1 to 5 times 10 to the negative 10th meters. 100 to 500 picometers if you're a picometer fan. They came up with a new unit for this too. It's called the Angstrom. So if you're at the atomic scale, you can be between 1 and 5 angstroms, 1 times 10 to the negative 10th meters. Down there, the little flavor text at the bottom, in 1989, back when I was in high school, a guy named Don Eigler was able to actually arrange atoms on the atomic scale. Really big deal. I actually remember when this happened. It was kind of a neat story. And I was able to find a video that I'll link to the bottom about in the ensuing 20 years after that, you know, what does that mean in terms of atomic accomplishments, which is kind of fun. Again, for many of you, this will be a review. The idea of the atomic number is the number of protons. Each element has its own unique atomic number. This is a really critical number. It's absolutely essential that you understand that this is the number of protons. And the number of protons is so critical because it determines the identity of the element. If you change the number of protons, either through some kind of atom smashing or through some kind of radioactive decay, then you change the identity of the element. That's the only way alchemy works. Now, in a neutral atom, the number of protons have to equal the number of electrons. If they're not equal, then you've got an ion, and we'll talk more about that next time, I should say. Atomic mass is the protons plus neutrons. Now, some people call that mass number. Some people call that atomic weight. I like the term atomic mass myself. So the number of protons plus neutrons equals the atomic mass. So to find out the number of neutrons, use addition's tricky friend, subtraction, and you will have it. So let's just fill out a chart for fun. Chlorine, obviously the atomic number equals the number of protons, so that would be 17, right? The difference would be the number of neutrons, and again, the number of electrons would be the number of protons. So feel free to pause the presentation for a second, see if you do the same thing for lead. I will wait for you. Welcome back. All right, so the number of protons equals 82, the difference 125, and the number of electrons 82. So that should be super easy for you to do. Make sure you've mastered that really basic skill. Now, why aren't they whole numbers on the periodic table? Tune in next time and we'll find out. So that's again, a kind of a blitz of a lot of atomic basics. I hope you got something out of that. We really appreciate you watching, and have a great day.